So if I plug in infinity on top and the bottom, can y'all see that it is infinity over infinity? So whether it's infinity over infinity or 0 over 0, that's considered indeterminate, meaning we have to use L'Hopital's rule. And just as a reminder, L'Hopital's rule basically states, derive the top and then independently derive the bottom, and then plug it in. So let's go ahead and apply our L'Hopital's rule. So we have the limit as x approaches the infinity. So we're deriving the top only. So let's do a quick reminder on natural log derivatives. It is 1 over the argument times the derivative of the argument, yes? So we have 1 over the argument, and that argument is this guy right here, e to the 3x plus x times the derivative of the argument. So let's kind of recall deriving e to the power of something. It is that itself times the derivative of the power. What is the derivative of the power right now? 3. So I'm just going to write 3 in the front, 3e to the power of 3x. And what is it, the derivative of x?
1.
Plus 1. On the bottom, I have x. That derivative is also 1. So I'm going to write this as 1 fraction. So we have the limit. I'm just simply simplifying on this one. Let's put 3e to the power of 3x on top, and then whatever's already on the bottom. So now let's plug in the infinity again. When I plug in infinity on top, we get infinity. What do I get again on the bottom? Another infinity. So we have to use L'Hopital's rule one more time. So then we have the limit as x approaches the infinity. The derivative of this guy right here is going to be 9e to the power of 3x. Because I'm automatically multiplying by the power. Over, derivative of this one is going to be 3 e to the power of 3x. And then we have that plus 1. So if y'all remember, it's all about the highest power. So my highest power is these two. And if my highest power were the same, we played the coefficient game, meaning what is 9 divided by 3? 3, done. And that would even stem off of pre-cal or even algebra 2. The next graph we actually have seen on our exam review, first semester exam review, and also on the exam. Oh, not this one, 27. Okay, does that picture look familiar? Very familiar. I think I made one that was kind of inverted as well on the review. So the given information is our f prime. So the first thing, let's see, Holland, go ahead and read.
The graph of f prime, the derivative of the function of f, is shown in the figure above. Which of the following statements must be true?
Okay, so if the derivative is given, it's automatic that it is continuous. So we know 1 is automatic. So it says which of the following must be true. So I have to contain 1 so I can eliminate D. Are we good with that one? Okay. And then it says it is decreasing on the interval from A to B. So let's kind of look at this. So what's given is our f prime. If f prime is negative, then it's decreasing. Is it negative everywhere? No, it's positive up here, and it's negative over here. So we know that's not it. The next one, we're looking at concavity. So we know the graph is concave up. If f prime is increasing, and it's concave down if f prime is decreasing. What is happening to our f prime forever? F prime is decreasing, so therefore f double prime tells me we have a concave down, so that's going to be true. So that's going to satisfy, let's see. You can even say it's concave down when f prime goes from positive to negative, and it physically is going from positive to negative, okay? So there's like multiple ways to look at this. All right, let's go on to number 28. 28, I believe we're going to use Fuiki. So Mia, let's read.
An isosceles right triangle with legs of length S has area A equals 1/2 S squared. At the instant when S equals square root of 32 centimeters, the area of the triangle is increasing at a rate of 12 square centimeters per second. At what rate is the length of the
So let's draw the isosceles right triangle. And they're wanting us to use our sides. And I'm going to use C as in our hypotenuse, as in a squared, b squared, c squared. So let's start by writing out our acronym. We have our FWIGI. And just as a reminder, F stands for find. So it asks us to find how the hypotenuse is increasing. So this is going to be dc over dt. And then when it's going to be our given value, it says when my side is radical 32. Side is radical 32 centimeters. And because I'm thinking ahead, I'm going to go ahead and simplify the radical. 32 inside radical, I could do 16 times 2. Is that right? And 16 is a perfect square of 4. Radical, no, is it 2? Yeah, it is 2. Silly. And then there is a given rate at a rate of 2 square centimeters per second. And that was the area of the triangle. So dA over dt is 12 centimeters squared per second. And centimeters squared is not random. Area is represented by squared, and that's why that's been consistent. If it were to be volume, it'll say cubed. And then the equation that we're going to derive is going to be the equation given. Area is equal to 1/2 side squared. And we're deriving this implicitly. So let's do a recall. Derivative of A is 1, and we always put dA over dt is equal to. When I derive the next one, 2 is going to cancel the half, correct? So I'm just going to have S, and 1 less of that 2 is understood 1 that I'm not going to write out, and we need ds over dt. So let's plug in what I know. I know dA over dt is 12. That was by the given. I also know my side is radical 32, that I'm going to use for radical 2. Then we have ds over dt. So when I divide, we get ds over dt. So 12 divided by 4 is 3, and the radical still 2 stays on the bottom. And you might think, how is that going to help us find the c value? So if the rate on my side is 3 over radical 2, and then the other one's identical because we have isosceles, can't I use Pythagorean theorem for that instant, what the c value might be? So let's do a recall in the Pythagorean. It is the component squared of the same value squared is equal to c squared. And when I square the 3, we get a 9. And when I square the radical 2, 2 pops out. And we already have a common denominator, which is nice. 18 over 2 is equal to c squared. So that means c squared alone is going to be what number? What is 18 divided by 2? 9. But then I'm looking for c, so when I square root the 9, we get, boom, done. If any might be challenging on the 5 that we're looking at, it'll be number 29. This is going back to like a lot of pre-cal stuff. All right, Samir, let's read number 29.
The graph of which of the following functions has exactly one horizontal asymptote and no vertical asymptote?
So let's underline one horizontal asymptote and no vertical asymptote. And I'm going to start with no vertical asymptote. And then I'll go on to the horizontal part. Because the vertical asymptote, I can eliminate 2 things. So let's kind of recall. There is a vertical asymptote when my denominator is equal to what? 0. So let's focus on that. Is there any chance I can plug in some value of x and then square it and then add it to get a 0?
0.
This number is always positive, correct? So this number is always positive because when you square something, it's going to become a negative number positive. So then let's look at this one over here. Is there a number or variable x that could make this denominator equal 0? Negative 1. So that means when x equals negative 1, negative 1 all cubed is equal to negative 1, and that's going to make, when I add 1, 0. So we know b is gone. We do not want a vertical asymptote. And then for c, again, let's analyze the bottom. Can I somehow make e to the power of something equal 1?
Yeah, probably.
When x equals what?
0.
0. Because e to the power of 0 is equal to 1. And when I subtract 1, it's going to be 0. So we have a vertical asymptote. And We know e to the power of something is always positive. A positive plus another positive cannot equal 0. Good? So that part is done. Second part. Horizontal asymptote basically means if I plug in a very large number on both directions, we're going to reach the same number. Is that right? No matter what. So because I don't want to look at a big number, I want to look at 10 and negative 10. So for this one, let's plug in 1 over 10 all squared plus 1. And that's going to give us, is that 1 over, what is it? 1 over really big number, right? I'm just going to say some big number. So if it is, what's up? You can use 100. It doesn't really matter. So if you basically have 1 divided by some big number, what number are you possibly getting closer and closer to? 0. Okay. Now let's plug in negative 10. We have 1 all over, negative 10 all squared, plus the 1. Isn't that in the same boat as the first one? Because when I square the negative, that's going to give me 100 plus 1. And that idea is still the same. 1 over very big number is approaching 0. So here I have 1 horizontal asymptote. So you can automatically pick this if you want, but if you have trust issues and you want to check the next one, that's fine too. So let's go ahead and plug in 10 again. 1 all over e to the power of 10 plus 1. This one again is going to be 1 over a really big number, which is approaching 0. Let's go the other way around. 1 all over e to the power of negative 10 plus 1. This is going to control everything. That gives me 1 all over 1 over e to the power of 10 plus 1. This number is going to get infinitely bigger, meaning it's going to reach 0. What is 1 over 1? 1. Do we all have the same horizontal asymptote? No. So it's got to be 8. So this one was quite in-depth, but that's the easiest way I could explain it. Okay? Okay, let's go on to our last one. On our last one, Bailey, let's read. We're on number 30.
For a certain continuous function f, the right Riemann-Sum approximation of the interval of 0 to 2 f of x d of x with n subintervals of equal length is 2 parentheses n plus 1 times 3n plus 2 over n squared for all n. What is the value of the interval of 0 to 2 f of x d of x?
So the first thing that we have to do on this one is define the integral. So if y'all remember finding area under the curve, we made like infinite amount of vertical lines or horizontal lines, right? Infinite. So that really in the end meant we were looking for the limit when n is equal to the infinity. So again, this is going to have to do with high over low, low over high, or what was the other? Same. There's an easy way to go about this one, or if you have time, you can be miserable and distribute the 2 and double distribute. But I'm going to give you a shortcut. You take these 2 numbers, will give you the highest power, because it's all about the highest power. So if I have 2n squared times 3n, it's going to give me 6n what? Squared. That means no matter what you multiply on the top, all the other numbers are going to be lower degree, okay? Which I don't want. And then we have already 1n squared. Again, this one is the same, so we play the what game? Coefficient game. So 6 over 1 is 6.